Now, we're going to actually, in Chapter 7, talk about similarity rather than congruence of triangles. Now, ratio and proportion is a concept you learned back in elementary school in 6th grade, so you're more than welcome to skip ahead to Section 7.3 if you need to. But we're going to start with ratios and proportions and go over a few examples. Now, we are just going to skip around and do a few examples. You all know a ratio is a comparison of two numbers by division, so we're going to look at example 2 here. It says that the ratio of side lengths of a quadrilateral are 2 to 3 to 5 to 7. And its perimeter is 85 feet. What is the length of the longest side? Here's the great news. If you know their ratios, we can just let each side, for example, be 2x, 3x, 5x, and 7x. Because if we simplified the x's, you'd be left with 2 to 3 to 5 to 7. If we add these all up, we know we get a perimeter of 85. So we add them together and solve, and you will get 17x equals 85. Divide by 17, x is 5. Well, we want to know the longest side, so that would be 7. 7 times 5 would be 35 feet. In this next example, we're going to solve the proportion. As you already know, solving proportions can be solved by doing cross multiplication. So we're going to multiply here x plus 2 times x plus 2, which gives us x plus 2 squared, equals 24 times 6, which gives us 144. Now, you are more than welcome to take x plus 2 times x plus 2, get a trinomial, and solve this by factoring. But remember, since the square root is by itself, you can use the square root property to take the square root of both sides. That's going to give us x plus 2 equals the square root of 144, which is plus or minus 12. I then subtract 2 on both sides, and x equals 12 minus 2, which is 10, and negative 12 minus 2, which is negative 14. So my answers are 10 and negative 14. 7.2, which we're going to quickly go over, talks about ratios in similar polygons. As you already know, figures that are similar have the same shape but not the same size. You also should know that two polygons are similar polygons if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. So as you can see here, we have a trapezoid and a larger trapezoid. And you can see that we have 4 angles in each, so all of your angles correspond. All of the corresponding angles, for example, angle A and angle E, angle B and angle F, angle D and angle H, and angle C and angle G are all congruent. We also know that every side can be written as a ratio, which would equal the same amount. So their ratios are equal. Now, if you are talking about a similarity ratio is the ratio of the lengths of the corresponding sides of the two similar polygons. For example, the similarity ratio of triangle ABC to triangle DEF, all the sides are 3 to 6, which would be 1/2. However, if I started with the larger triangle and I said the ratio of triangle DEF to triangle ABC, we would say 6/3 or 2. Now in example 2, all we're going to do is determine whether the polygons are similar. If so, write the similarity ratio and a similarity statement. Since we know that these are both rectangles, all angles are congruent, and then if we write ratios of, for example, PQ to TU and PS to TW, you will see that their ratios are not equal. Therefore, these rectangles are not similar. In B, we have 2 triangles that we want to see if they're similar. In B, in these triangles, if you look and you write all of the sides, for example, 18 divided by 24, 12 divided by 16, and so on, you will see they all have the same ratio. So we can use side, side, side similarity to show that these 2 triangles are similar. Alright, so now that we've gone over all of the review, here is the new information. Section 7.3 talks about triangle similarity. There are several ways to prove certain triangles similar. The following postulate, as well as side, 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 and side angle side similarity theorems, will be used in proofs such as side, 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 angle, hypotenuse leg, and angle side were used to prove triangles congruent. Basically, it's the same thing you did in chapter 5, but instead of proving triangles congruent, we are going to prove them similar. So let's go over the first one. This one is called AA similarity. AA similarity states that if you have two angles of one triangle that are congruent to two angles of another, then the triangles are similar. Now make note that they actually still might be congruent, but we know they're similar as well. So we know that if two angles of one triangle are congruent to two angles of another, then the triangles are similar. So triangle ABC is similar to triangle DEF. So let's look at example 1. I want you to explain why these two triangles are similar and write a similarity statement. Well, let's look at what we have. We have two parallel lines. We just have to prove that two of the angles are congruent. Well, we know vertical angles are congruent. We also know that because these are parallel, we have a transversal, pick one, and by alternate interior angles, angle P is congruent to angle R, or you could even say angle T is congruent to angle S. Here's one example that you could say. Since segments PT and SR are parallel, angle P and angle R are congruent, and angle T and angle S are congruent by alternate interior angles theorem. Therefore, our statement would say angle or triangle PQT is similar to triangle RQS by angle-angle similarity. The next theorem is side-side-side similarity. It sounds just like congruency. If you have three sides of one triangle are all proportional to three corresponding sides of another, then the triangles are similar. The next thing, Theorem 733, which is side-angle-side similarity. Side-angle-side. If two sides of one triangle are proportional to two sides of another triangle, and their included angles are congruent, then the triangles are similar. Just like side-angle-side with congruency, similarity also works. In example 2, we want to verify that these triangles are similar. In A, we want to show that triangle PQR and triangle PRS are similar. So we match up the corresponding sides. So PQ matches with PR, so that means we could write that as the ratio 4/6. QR corresponds with RS, and we can also write that as 4/6. And lastly, PR corresponds with PS, and that would be 6/9. If you simplified all of these, you would get 2/3. So because of side-side-side similarity, we can say that triangle PQR is similar to triangle PRS. In the last one, we want to prove that triangle JKL is similar to triangle JMN. So let's match up what we know. Now, these are overlapping, so we could redraw the small one and the big one. So this would be 2, this would be 3, this would be 6, this would be 9. So we could write the ratio of those two sides as 2/6 and 3/9. 2/6 is 1/3, as is 3/9. So we know that 2 and 6 and 3 and 9 are all similar, and because these share the same angle, by reflexive property, we know that side-angle-side similarity would prove these two triangles similar. All right, in example 3, we want to explain why these two triangles are similar, and then we want to find BE. Step 1, look at the problem. We have to look at and make sure we understand that ABC is going to be similar to DBE. So AB aligns with DB, and BC, segment BC, corresponds with segment BE, and lastly, segments AC and DE also are corresponding. So right off the bat, we know that these are similar because once again, segment AC and segment ED are parallel. Therefore, by alternate interior angles, we have Angle similarity, therefore they're similar. Find BE, so we have to write a ratio equals another ratio, which will be a proportion. 36 is corresponding to 54. And then 54 corresponds with x. So we cross multiply. Easy. 36x, 54 squared is 2,916. Divided by 36, x would equal 81. Therefore, the length of BE equals 81. In example 4, we're going to actually write a proof. So here's what we know. A is the midpoint of segment BC, and D is the midpoint of segment BE. I want to prove that triangle BDA and triangle BEC are similar. Step 1, write the given. We know that A and D are both midpoints of the sides of that triangle, BC and segment BE. Because of the definition of midpoint, we can say that segments AB and CA are congruent, and segments BD and DE are congruent. And I'm going to now mark that on my picture. Then I can say that their lengths are equal because of the definition of congruent segments. Now what I'm going to have to do is show that each side of the triangles are proportional. So I have to show they're proportional, so I have to add these together. So now what I'm going to do is this. The segment addition postulate would say that AB plus AC equals BC, and they wrote that backwards, which is fine. BD plus DE equals BE, segment addition postulate. Now, all I'm going to do is plug in. Look at what they did here. For AC, I plugged in BA. For DE, since DE equals BD, I plug that in. So now from there, what do you think you're going to do with BA plus BA? You're going to simplify, and BD plus BD. I simplify because I'm going to have to show they are proportional. So that would give me BC equals 2BA and BE equals 2BD. Now, look what I did. I solved, and I got the 2 by itself. I divided this first one by BA. That gives me a ratio. BC divided by BA is 2, and BE divided by BD is 2. What that showed me is this. BC, which is the length of the entire side over here, divided by BA, which is the smaller triangle, is 2. The same thing is true for the other side. Therefore, you just showed me that they are proportional. They have equal ratios. So look what I did here. Now, since they're both equal to 2, by transitive property, you could also use substitution, by the way. Since this equals this and this equals this, you can use substitution or transitive property to show me that the ratios are equal. So I now already have what? I have two sides that I can show their ratios are equal. There's one last thing you have to show. I'm going to have to show that angle B is congruent to itself by reflexive property. So then angle B right up here is congruent to itself, and therefore by side angle side similarity, I can show that both of these triangles are congruent. The last problem, example 5, shows the photo of a gable roof. Segments AC and FG are parallel. Use similar triangles to prove that triangle ABC is similar to triangle FBG. It's very similar to the last problem. And then we want to find BF right here to the nearest foot. So prove them similar. So what do we know? Step 1. Now, it doesn't say to have a proof, but I'm going to write this down. As we know that the sides are parallel. And that's the given. We can then say that angle BFG is congruent to angle BAC. BFG, this angle right here, BFG, is congruent to angle BAC. Why is that? Because they're corresponding angles. We know that these are parallel. So angle F, and you can, well, you can't call it angle, yeah, you could call it angle F. Angle F and angle A are congruent. We then could say, now you could also say the same thing over here. You could say angle G is congruent to angle C, and then by angle similarity that would be fine. But you could also say angle B is congruent to itself because of reflexive property by the same thing, angle similarity. Now the second part is finding the length right here, I'm going to put x, of BF. Now the problem is the entire side is not 17. Just this piece is 17. So you have to write a ratio from BF to BA. So we know BF is x. Now BA though is x plus 17. Since this piece is 17 and this piece is x, the entire thing is x plus 17. Now we can write it as the other side here, which would be 6.5 over 24. So 6.5 divided by 24. We then solve this by cross multiplying. That would give me 24x equals 6.5 times x plus 17. So we distribute 6.5x plus 110.5. And we just solve it. That gives me 17.5x equals 110.5. Divide both sides by 17.5. That would give me x as approximately 6.3. So BF is approximately 6.3. And lastly, back in chapter 2, you learned the reflexive, symmetric, and transitive properties of equality have corresponding properties of congruence. These properties also hold true for similarity of triangles. For example, reflexive property for similarity can prove that a triangle is similar to itself. Symmetric property could say that triangle ABC is congruent to triangle DEF. Then we would also know that triangle DEF is similar to triangle ABC. And lastly, transitive property. Triangle ABC is similar to triangle DEF, and triangle DEF is similar to triangle XYZ. Then we know that triangle ABC would be similar to triangle XYZ.